All right, welcome back. So we were talking about all the bad things that computers have done or could do, and we ended last time talking about how to make sure that a program's going to do the right thing, to have some confidence in it. And we talked about making tests to ensure that, well, at least some of the time, it's going to do the right thing. Okay? You might be wondering, is there anything we can do that's better than that? And there are a few methods that people like to use, especially in very critical software like avionics or, I don't know, probably shooting rockets into space like SpaceX does. Everybody's doing something fancy in those fields, and let me walk you through the different ways that you can make correct software, or highly believed to be correct software, that is. One way to do it is to check yourself every time you run a program. It's called redundancy or self-checking. It's programs that end up checking their own outputs. So, I don't know, let me represent your program by a box that I call P. You give it inputs, and of course it's going to give you an output, maybe multiple things. And it's your job to check, like, okay, if the output was 42 based on my input, was that good enough? Maybe you need to make sure that the output was, I don't know, greater than or equal to 25, that it's not odd, things like that. These are things that you could check about your program. This might be requirements on the output of your program. And so after you get the output, you then run these checks on it, making sure that it actually did the right thing. And if it didn't, maybe you crash, maybe you use a different backup version of the same program, things like that. But that's one way to at least make sure that what you tell the user is it follows all the specifications. Okay? It meets the specifications, that is. So that's one way to do things. Let's now talk about proving things. So there exist some fancy programming languages that you can go and prove things about them. So any program that you write in one of these languages, you can then make sure that it does the right thing. It can be mathematically proven for sure 100% of the time it's going to be right. So if you want to get down and dirty with math, you might enjoy proving things about your programs. And one of the most popular ways to do it right now is using things called proof assistance. And this one is, well, it's a French word, so it's, I guess, technically pronounced coq. And it's very popular these days. People have made verified compilers, if you know what that means. If you take CSCI 40, you will. They've made it so that they know that when a compiler outputs machine code for your program, the ones and zeros that make it run, it's always going to be right. It's always going to do what you expected. Okay, so let's move on now to analyzers. Analyzers, I would say, there's a little bit of a line between them and proofs. Proofs are like the best thing that you could hope for. Your program's always going to be right. Analyzers, they are built on top of a lot of math. So it's like you're running a program inside of math, and you see if there's any issues. Like you have a box. You have your analyzer box. And you actually feed it an entire program. So you give it that program P, and it thinks for a while and outputs like, oh, yeah, this program, it will always make sure that the output's greater than or equal to 25. Guaranteed. Okay, so there's some things that it can say about a program, but other things it has to be a bit vague about them. Okay, so that's what an analyzer is. It's a box that takes programs and tells you things about programs without actually running them. Okay, that's fun. Another thing that you can do to make correct software from the start is to specify it well. There are languages that are not programming languages, languages that don't get run, but they're languages in which you can write a specification for your program. Like, it's supposed to do this. It's supposed to always have an output greater than or equal to 25. It's supposed to have an output that's never odd. Okay, that's the idea. One of them is called Z, but I think it was made by Europeans, so it's called Z. And yeah, it's where you say what you want to be done, and then you then write the program in a language, and then you use another method to go and prove that the specification like holds up. Like, your program lives up to the specification, that is, the other way around. So that's another thing that you can do. The issue with most of these is that you can go wrong at the verification stage. You can go wrong at the specification stage. You need to specify exactly what your program needs to do. And that's really, really hard. Okay, it's harder than you think. And so your specification can still be wrong when, in reality, the rocket's going to crash if it's ever less than 30, it turns out. So this greater than or equal to 25 wasn't right. So if the specification's wrong, there's no real use in any of this stuff. And that causes issues. So there's no good way to do things. There's no good way to write correct software. You've been writing your own now for a while, and you know how hard it is. But there are some ways to make it better, and here are a few. Okay, let's move on to some more stories now, and then we'll analyze technology. So the first thing that we should talk about, it's from the book, air traffic controllers. They are watching you like on radar. They got, I guess it looks like this, a bunch of dots on a screen, and here are all the planes passing by with their relative elevations. They know their current headings, and it's possible that some of them might crash. So air traffic control is trying very hard to route all these planes around each other, but sometimes there's still issues. And so now they put boxes in planes that try and tell you how to avoid collisions if you're a pilot. So it's called the Traffic Collision Avoidance System, or TCAS, or however you pronounce that. And it can go and look at where you are. It has your GPS location inside of your plane, and it can look at all the other planes that have little beacons that tell you where they are relative to you, and it can go and figure out if two planes are about to hit each other. And it goes and tells pilots, okay, yes, because the two boxes in each plane, they talk to each other. So it's like, this one, increase your altitude. This one, decrease your altitude. You'd crash otherwise. So do that. Unfortunately, this kind of cried wolf a bit when it first came out. So the original version, the original version of this software, or this hardware and software, I guess, it had a bunch of false alarms. So it was like, okay, this plane's way over here, maybe, and it's going this way, but it says like, okay, these two are going to crash or something. That's a problem. And so people stop believing it. And obviously that's an issue. Because eventually, this got really good. Like, they improved the software. It started becoming really, really accurate, and it was a sight to see. So, an issue happened with this because a pilot followed the system. It told him or her to increase in altitude or something, and it told the other plane to decrease in altitude. But the other plane that was told to decrease in altitude, it was instead talking to the air traffic controller, who told them to also increase their altitude. And so that was a huge problem, and now every pilot is required to disobey the air traffic controller and trust the system instead. It's that accurate now these days. So that's a good story. It took some bad things to get to that place, but we're a bit safer now in the air than we were, I would say. Okay. With all of this, all these slides, we've talked about issues. And one of the easiest solutions is just rip the computer out of the wall. We don't need that, right? Maybe we depend on computers way too much. Well, should we just stop using them? What's the point of them? Is it a good idea to use computers for all these things that are running our lives and in control of our safety? So let's ask our boys. Kant, well, it always depends on the question we ask these old people. Maybe the question is, should we use computers to make every task easier for us? Should we always look to computers to solve our problems? That's the kind of thing we could ask Kant with the always being the key thing. And he might say, well, no, he believes in free will. Like, if you don't want to use a computer, you don't have to. If you don't want to use that box in your plane and you just want to look at the ground, look around you, make sure no planes coming into you, that is your prerogative. So I think Kant would be about you making your own decisions about technology. Whereas Mill, or a utilitarian, might be like, well, what does this do for us? Does it make our lives better? And I think usually it does. Like, it's going to save your life more often. It's going to do good things. Eventually, once we work out all the kinks, that is. So, Mill might say, utilitarian might be, yes, it's going to improve our lives eventually. And so we should depend on computers. Maybe we could have backups. I think there would be no issue with that, but a computer is making all of your lives a bit easier right now. It's making it so that you can go to school. So I think I would side with the utilitarians right now. I'm a bit biased because my entire career revolves around computers, but I think I'm in the Mill camp. And then finally, if my argument for this slide for utilitarians is all about it's improving our lives, it's making things safer, let's talk about how it's done that. This would be a beautiful thing to give to you in class to talk about. All right, let's have a debate. But you get to just listen to me drone on now. Sorry about that. I hope you're listening to this at like 3 times the speed. So, do computers make us safer? If so, how? Let's talk about cars. I think that's a great example. So, you have safety belts, which are completely mechanical, right? So they're not really doing too much for you. You can buy an old car, it doesn't really have many computers inside of it. And it gets you around the town just fine. But computers have made cars safer for a few reasons. The first is, and probably the biggest one in my mind, is ABS, anti-lock brake systems, right? So there's a little tiny chip in the computer, or a little tiny chip that is a computer inside of your car, if it's a more recent car, and it's going to like pump the brakes for you if you ever slam on them to make sure you don't skid, and that gets you to a stop sooner, right? I'm sure we all learned about this when we were getting our driver's license, and so that's a beautiful thing to have. And the second thing that your car usually has these days is at least a check engine light. Sometimes that's mechanical, like back in the day maybe it was, but a lot of the time, like even on like cars made in the 90s, there was a little tiny computer that booted up when you turned on your car, and it told you things about it. Like it ran some tests. It was like, okay, yes, the pressure's fine here, everything's okay, or no, something's wrong, and then you can take it to somebody who has like a little reader for that chip, and a shop can tell you like, oh yes, the engine light came on because of this reason. This was the problem, and let's go and fix that now. Okay, that's one way. That's cars. Airplanes. Well, you got your autopilot. I think we've covered this already, at least with TCAS. That's keeping you safer. Autopilot, I could argue, I think we could argue that keeps us safer as well. It's like keeping us on course. It's not going to let us drift off somewhere if the pilot falls asleep or something. And I think we could talk all day about this stuff. Home security systems, things like that. They make you personally feel safer. Like you can see your porch whenever you want because you have a camera there. Okay? I guess I don't need to write anything there. And what was the best security system before electronics? Probably just a bunch of dogs, right? So, sometimes the dogs fall asleep, that is. So, I would say that computers do make us safer in some ways. And I'm sure you can give me plenty of counter-arguments, too. and I would love to have heard them in class. Just a few more phone passcodes. You've written now about going to the airport and having your phone, like someone forcing your phone to be unlocked. But most of the time, like if you drop your phone somewhere and somebody picks it up, they can't like look at all your pictures or something because you have a passcode on it. So I would say that's like guarding your personal information. And same with online banking. Like it's possible. I mean, there are little phishing scams and things like that to go and try and steal your password. But online banking is you have a password, and it's making sure that it's always you who logs in and does stuff with your money. Like sometimes there's two-factor authentication. So they make sure that it's you, like, because they send you a text message. It's you that logged in on this new computer. Whereas, I don't know, you could probably put on a disguise, or if you look like somebody, you could steal their ID and go to the bank, and you're them now, and you can take out all their money. So I would say online banking keeps your money safer, maybe. So there's plenty of counter arguments too, but I think this is where I want to leave you here with these slides. So we've talked about the good and the bad, I would say, of computers. And so I guess it's always up to you. There's no right answer. Do you trust them? Okay, so that's it for these slides. We're going to be like in between for a few lectures now. Sorry about that, but it should make sense. The next slides are about artificial intelligence, which I'm really happy to talk about. So first of all, I want you to meet my cat. His name is, I call him Alonzo, but his full name is Alonzo. He is named after Alonzo Church, and this man had a lot of influence on my eventual graduate studies. So I am paying homage to this man by naming my cat after him. He is the inventor of the most beautiful model of computation, even though I didn't talk about it at the start of this class. He's a little less known, but in my little subfield that I specialized in grad school, he is like a god. And he was also Alan Turing's PhD advisor, believe it or not. So he's at least famous by association. Okay, so with that, let us move on now to artificial intelligence. And to get there, we need to talk about computers and how fast they're growing. Okay, so the question that I want to answer for you is, how fast are computers getting faster? If that makes any sense at all. Because they are. Why would you buy a new one if it wasn't better in some way? And usually better means faster, right? So back in the day, this guy who worked at Intel, who founded Intel actually, his name's Gordon Moore, and well, he realized, or like he wrote it down, like he was the first person to state this observation and this hypothesis. He noticed that the number of transistors in a chip doubles about every 2 years. So if you start one transistor, eventually you get to 2, 2 years later. After 4 years, that's now 4, then 8, then 16. That's exponential blow up. It's like, whoop. It's getting really, really big. And transistors do cool things. They are what our computers use to think. Okay, that's our CPUs, the brains of our computers, are made up of a bunch of transistors just working together to perform some computation. And if you have more, you can do more things. Okay? And so for a while, this also meant that, well, double the transistors, your computer's also getting twice as fast. It can do more things faster as well. They improved on the CPU design and things like that. So computers got twice as fast. And then eventually, I guess in the past maybe 15 years, I would say, starting 15 years ago or so, we started running into power limits for processors because you can only put so many transistors in a certain amount of space. And if you want to make that space wide, then you have to suddenly plop a lot of power into your machine. It gets bad. So we don't want to have to pay just as much to run a computer as to run our air conditioning. So eventually we started using multi-core processors instead to try and get a better speed up. So it used to be just you got one core. That is your computer. It does it works on one thing at a time. It just swaps in and out computation. But now we have multiple cores. Like maybe you've heard of like, I have a 4-core machine. That's the requirement for Zoom if you want to have a background. You have to have at least a 4-core processor. Quad core, they say, for example. And I guess the way that they got around the power limitations is they kind of stacked them. Like it's easier to do stuff. Like boop, boop, boop. Where they kind of stack things on top of each other. Easier to move electrons around, apparently. Not my area, though. I'm not really sure. So, multi-core is now a thing. And so, the speed of the processor, though, it never really increased for a while. It hasn't. Like maybe you've heard of, like, my computer has a 2.1 gigahertz processor. Same was true in like the early 2000s. So that didn't increase in speed for a while now. But the number of transistors still has, and the reason our computers are still slightly faster is because they can do more things at once with multi-core processors. Okay. The bad news is this cannot continue. This trend for doubling these transistors, it cannot continue because the transistors are now getting so small that we are hitting physical, like quantum physics issues. Like atoms are like playing a problem. So you can only hold so many electrons in a few nanometers, and suddenly we have issues. So we're about to hit a wall, but it's been a nice ride. Okay, so that's my fun story about this. And so let me show you this. If I can zoom in a little bit, that would be even better. So, oh no, this is not going to be easy, is it? So, here's the title. Moore's Law, number of transistors on integrated circuit chips, starting in 1971. So, here is a logarithmic scale y-axis, transistor count. And oh man, did it start pretty tiny. So back in the 70s, we had about 2,000, 2,500 transistors on a single chip, and it was still doing stuff, still doing useful stuff for us. Oh no, this is not going to be easy. Sorry about this. Come on. There we go. There we go. Okay. And then suddenly, remember that this is a logarithmic scale, so a line means if it increases in a line, that means it increases exponentially, really. Because it jumps from 10,000 to 100,000 to a million. So eventually, you can see that Intel got in the game quite early. Intel and Motorola were at each other's toes for a while. Then suddenly, Intel kind of won out. ARM came into play. That's what our phones have. Dun dun dun. Until we get to today, which is, I guess, 2018 was the last thing on this slide. But we start having millions of cores, and that's beautiful because it allows our programs to do multiple things at once. And this is about where we are. Eventually we're going to hit a wall, and it will be quite soon nowadays. And you can see this is kind of started to level off. The line is still a line almost, the trend line, but it's not as steep as it was over here. You can see the difference, I think. But we're still following the trend for now, and it's fun to think about. Okay, so that is computers getting faster. And what does that mean for computers thinking? Well, if they can work faster, maybe they can think like a human. And eventually surprise us and convince us that they are humans, maybe. Okay, so artificial intelligence. How can computers think? How are they even good at it? So AI is the shortened version of that, artificial intelligence. And just the definition is, well, it's when machines think. Your computer takes in its environment somehow. If it's an artificially intelligent machine, it's going to take it in its environment, like this robot is doing. Like it's got a little sensor, it's looking that way. It has sensors on its feet probably. It knows what angle all these things are at, like how soft the ground is maybe because it needs to run. And maybe it has some radar coming out of it right here. It's trying to figure out, hey, this thing that I'm looking for, is it over here maybe? And then it's got plenty of other things that I don't know about because this is proprietary technology. All right, so artificial intelligence, it's when machines think. So they're taken in their environment somehow, they're given some kind of data, and they have a goal, they have an end goal. Like maybe this one's goal is to like jump up on top of a box and retrieve an object and then jump back down, perhaps. And it does that all on its own. So there's plenty of little subfields of AI, of artificial intelligence. You have your robotics, and this is a Boston Dynamics robot. Please go and look them up on YouTube. They have weird-looking robots that do weird things. But that's artificial intelligence. This robot is thinking for itself. Then you have things like machine learning, big data, things that you might have heard before, that do things like face recognition, and so on and so forth. And I'll talk about examples of that. Then you have things called neural networks, which is a type of machine learning. It's a way of training a machine learning model, and I'll give you some ideas about that and a little intuition. Consider becoming a computer science major if any of this is interesting. And then you have what might be more boring, but this is really essentially what machine learning is, artificial intelligence. It's just applied statistics, really. And so even at like UCSB, where I came from, their stats department is now like data science department, things like that. So everybody's riding this hype train, artificial intelligence, machine learning. It's really just stats. It's just fancy stats. So now you have a reason to pay attention in your stats class if you didn't before. All right, so let's look at some cool examples of artificial intelligence. This is like, this portion of the lecture is more like history and like to get you excited. So you have some background knowledge when you need to maybe write about this stuff. All right, so the first thing is, the first thing that probably touched your life, or maybe your parents' life, is back in the day when they came out with the first digital cameras. Boop. They, on the back of them, on their screen, they were showing you like the picture that you just took maybe, and they had all the faces. And sometimes, like right before you took the picture, first of all, it like put all the faces in a box. That was like the coolest thing back in the day. And then it also tried to figure out if somebody blinked while you took the picture so that you could retake it immediately, while everybody was still standing next to each other. So this is artificial intelligence. It's blink detection. It's machine learning. It's a machine learning technique. And what it's going to do is it's going to find all these features of a human's face. It's going to, all right, figure out where the face is actually. And then, okay, once it finds the face, usually humans are upright, so it'll probably look towards the top half, and then try and find some differences in color where you can separate the skin from the eye, things like that. That is perhaps what a machine learning model is doing. It's hard to understand them because they kind of learn on their own. And so there's a big difference between an eye being open and an eye being closed, and if I gave you like a couple days to write a program, and I gave you pictures of this portion of somebody, I think if you find enough white, you'll be able to conclude that, oh yes, the eye was open. And if you don't find much white, you'll notice that the eye was closed. So that is a way to do machine learning, perhaps. Okay? That's a way to have a computer do a certain task for you that is kind of like what a human might do. Like to perceive the environment, to look at a human's face and be like, oh yes, their eyes were closed. Okay? So here's a very large slide, but I want to tell you how machine learning works, because maybe this is weird. How does it know where the box is that it should draw? How does it know to put this green box right here and then start looking right here for eyes? How does it figure that out? And the answer is, I want to highlight the fact that computers are very dumb. We are trying to make them smart, but they really are at the beginning very dumb. So what we do is we train them. So like we are their coach, and we make a giant set of what's called training data. So we give our machine learning program a huge stack of pictures. Like here's my huge giant stack of pictures, just one on top of the other. And they all have people's faces on them. And we usually also label the data that we give to our machine learning program so that we tell it, okay, yes, this is a face, here it is, here's what you should do to that face. I want you to draw this box, just like that. Figure out how to do that, please. And you send it off to do its work. And so if you want to notice faces, you'll give it a bunch of labeled pictures with faces and non-faces. So you'll also, I don't know, give it pictures of like plants. And you'll be like, ah, yes, there is no face in this picture. There's no green box. So you somehow try and trick it. So there's not always going to be a face. Figure out the difference between a face and not a face. And when you do find a face, draw a box around it. So that's essentially the stuff that you have to give to your machine learning program, usually. And then the step 2 is the longest step, usually. You're going to train your model using some machine learning technique. Maybe you've heard of neural networks before. I guess this is a picture of that. It's like artificially modeling the way that neurons work in a brain. So that is essentially machine learning. It's really not that bad. There's a whole lot of fancy math that goes into it, but at a high level, it's not too hard to explain. The training is the longest step, usually, because the model that your machine learning program comes up with the first time really, really sucks. Usually, if you give it all the data again, or you had a different testing set, it'll be like, oh yes, there was a face in empty space, here's a face over here, here's another face sideways. So it's usually very wrong the first time you use it, but you keep training it. You give it a bunch of rounds of data, of the same data, of different data, things like that. And it starts to get better. It starts to notice like its mistakes. And that's what we call learning. Okay? And then finally, once you're comfortable with it, you test it on a separate set of labeled data, because maybe it's just memorizing the real answers for your test. Okay? So make sure it's not just memorizing the test data, because we want it to find faces, not, okay, yes, this exact picture has a face right here. That's not what we want it to learn. Okay? And it's usually very, very hard to get a ton of training data like this. And so many companies have popped up that do just machine learning, that just do data gathering. And now you know why so many services are free these days. So Google Photos, for example, it stores your photos for free. And the stipulation behind that, the reason Google's letting you waste its space, is that it wants your images. It wants to use them to train their machine learning models, among other things. So that is machine learning in a nutshell. I'd be happy to talk to you about this. Come to my office hours. It is a fun thing. It is, unfortunately, an upper division computer science thing, but I'd be happy to talk about it with you now. Okay, another example of machines doing human things and making choices. Factory robots. So, like, here's a car plant, and you have these robots working on certain specialized tasks to go and make that car. And the reason we came up with these machines to do this stuff is that they tend to be very, very good at doing the same thing over and over again. So a factory robot can just, like, doesn't have to wake up, it doesn't need coffee, it can just go at it, and maybe it needs oil a few times a year, but it can keep doing the same task over and over again with ridiculous precision. And so it'll do things perfectly with a very, very tiny chance of failure. And so it doesn't require a lot of upkeep usually. And once you write a program or like tell it how to do things in a way, it's gonna work perfectly for the rest of its of its life until its like parts wear out or something. And I guess up front this costs a lot of money to install these factory robots, but the second they are working, they start making a whole lot of money a whole lot faster, because now you don't have to pay somebody their salary, which is really unfortunate, but I guess that's one of the arguments for like what's it called? The thing where they give you a salary, universal basic income. That's the one. That's I keep forgetting that word, but that's the idea. So this is why eventually it's probably a good idea to have one of those one of these days, because robots will run the world eventually, won't they? So I'll talk about that when we get to the singularity at the bottom here. We might not get to that today. But okay, let's talk about something that you might have been aware of, or that's something that sounds like real machine intelligence. So there's this thing called Watson that you might have heard of. And this is probably what you think of when you think of intelligent computer. One that can talk, one that can understand speech, things like that. So this Watson, it's just a large supercomputer. Oops. This was just its screen is huge. And it was made by IBM, and they got the idea for it starting back in 2005, and they wanted to make a computer that could play Jeopardy. They're not happy with like programs that can play chess. No. They want a computer that can play Jeopardy. And so that was a very hard problem. And so what it needs to do, what Watson does, is it uses what's called natural language processing. And so it's going to parse a sentence. It understands words. It understands English. And it uses its knowledge of English and its programming to decipher the questions that are asked on the game show Jeopardy. And it answers them in the proper format, and it uses a huge database of information. And that database is gigantic. One of the things, for example, when it went on Jeopardy, it wasn't connected to the internet. It was just sitting alone with its giant database. It had the entire copy of Wikipedia on it, for example, among many, many other things. And I guess if we were in class, I'd show you this video, but feel free to play it yourself when you're watching these and looking at these slides. They put this computer up against a bunch of very, very famous Jeopardy contestants, and it beat them quite easily eventually. Like, there are obviously some kinks to work out in this guy, but it got good. And so that is a very nice success for machine learning. And just to give you an idea of the way Watson thinks is, first it reads like input. It can understand words and written text. Like, there's some written text, there's like, I don't know, there's some words that were shouting at Watson, W for Watson, and it's going to understand that stuff as a question, and it's going to look at its database. It's got a bunch of them inside of it, and it's going to come up with a bunch of possibilities, like with confidence levels. So more stats, of course. It's all just glorified statistics. Okay, it's like with a 95% confidence, I believe that the answer is A. With a 42% chance, I believe the answer is B. With a 3% chance, I think the answer is C. And if it's confident enough, it's going to shout out the answer that it's most confident in and make some money. Okay, so that is Watson. It's a fun little example. And my next example is like the granddaddy of artificial intelligence. When people were imagining artificial intelligence, this was one of the first things that they wanted it to do. So they wanted it to play chess. I'm going to include Go on this slide as well. But chess was the cool thing. Like, if a computer could play chess, we have made it as a society. Okay? And we got good at chess with machine learning back in 1997. That was the first time when a computer beat the world champion. His name was Garry Kasparov, and this is him. and this computer beat him. Back in the day, I forget what its name was. I think it had the word blue in it or something, but it learned how to play chess. It had a huge database of information. It knew how to look ahead in the game and figure out what might happen, and it learned how to play chess. And that shocked the world back in the 90s. Okay? And more recently, we've been doing the same thing with Go. So with a checkerboard or a chessboard, you only have so many squares, right? Boop, boop, boop. Not a whole lot. It's like, 8 by 8 or something like that? Go, if I remember correctly, is 19 by 19. It's a board game. And so there's a million more possibilities, or several million, billion, trillion more possibilities, that is. And it took until 2017 to beat a world champion there. And here's a video of that I probably would have shown in class if we were there. And one of the really cool things about how these programs learn to play chess or Go is that the rules of chess, the rules of Go, they're clear. You can program them. You can write them up in a day. Be like, okay, yes, knights move like this. Rooks move like this. Sorry. Rooks move like this. And, you got all these little steps that your knight with its horse can go and do. And this is your rook, it's long. Well, the idea is you can program these, and then your computer can go and play against itself because it knows the rules. It's like, okay, I'm going to pick, computer is playing the A player and the B player, the black and the white, and it's like, okay, I'm going to make this move, and it's going to play against itself. Okay, I'm going to make this move, and whoever won, it's going to realize that, okay, this one had the better strategy. I'm going to remember what I did here as opposed to here. And that's fascinating. This is computers being used to learn about their own, the things that they're trying to learn. They're teaching themselves. That's the idea. So that's fascinating. And I think that's where I want to stop today. So I'm going to go and write up your next essay, and I will be right back. All right, I have returned. Let's talk about your essay now. So let me make this larger so you can read it. It's going to be a 1,000-word essay, but it's going to be okay because you're most likely going to be quoting a whole lot of people. So you'll get up to those 1,000 words pretty quickly with all the quotes that you'll be doing. So I want you to find fallacies on social media. So go to Facebook, go to Twitter. There's plenty of places. And I want you to find people arguing something incorrectly using a fallacy. Okay? There are more fallacies than we talked about in class. There's a huge list on Wikipedia with some really nice explanations, and you're allowed to find any one that you want, including the ones that we talked about in class. And it's also not a requirement, but I would strongly encourage you to at least try and find a couple of fallacies about computer science issues. Okay, arguments about computer science issues that are fallacious. So things like, all right, robots will or will not take people's jobs. There's plenty of arguments about that may or may not be correct. Same with all this stuff like Facebook, Google, Apple, Amazon. Insert name of company here is evil for X, Y, and Z, things like that. And then, of course, other countries doing things to us or are not doing things to us electronically, things like that. Okay, that's the idea. So your main directions, write an essay with 1,000 words. I want you to use this kind of structure. So I want an introduction and a conclusion. This is an essay after all. But the paragraphs in between, and you can write the introduction and the conclusion as short or as long as you want. The meat that I want, though, I want at least 5 paragraphs, each containing one fallacy. Okay, each finding one social media post that you're going to quote, and then analyzing why and how it contains a fallacy. Okay, and the one last requirement is, if you go back to our slides, it's very easy to find ad hominem. That is super easy on the internet to find somebody being angry at another person. Okay, so that's the easiest fallacy to find. So please make sure that at least half of your posts have some other fallacy. Okay, so that's the idea. Just find a bunch of fallacies to fill up 1,000 words, and you'll write a paragraph for each fallacy, quote it, and analyze why it has that fallacy. Okay, shouldn't be too bad. Let me give you an example, and obviously you can't use this one now, but we will pick on the president. So here are a few tweets that are recent, and a few of these are like, we can make arguments for them, like maybe Biden would prefer to like downsize the military a little bit. That I could see this might be a true argument. But if we go back here, law and order, vote, is a false dilemma fallacy. Okay? It's making the case for, and you'll have to read between the lines for this one, but this tweet is essentially saying, all right, you vote for me, or you don't have law and order. Okay? That's the idea, and obviously that is not true at all. So that's a false dichotomy, that's a false dilemma fallacy. Okay, and so you'd argue being like, okay, this tweet is trying to say the fact that either you vote for Trump or there will be no law and order left in the country. That's essentially the point, and that's not true because it's quite possible to vote for any president, and no matter who got elected, every past election, there weren't like horrible things happening. There was always law and order, I guess, at least until you go back to maybe the Civil War era. But hopefully that makes sense as to why this is a false dilemma, and that's essentially what you'll say. So you'll quote this, analyze it, talk about what's wrong for your particular fallacy, and just write me an essay about all that stuff. And make sure that not all of them are ad hominem. Okay. One nice place that you might want to look is famous people's tweets in the comments, because now you have suddenly a bunch of people that are disagreeing. Okay, usually, or are agreeing incorrectly, for example. So that might be a nice place to look. With that, I think that's all I got for you. This is the longest essay yet, but I think because of the fact that you'll be quoting all this stuff, it shouldn't be too bad. And I hope it's fun. So good luck with that, and I will see you in the next lecture.